Hey everyone, it's Brian. Welcome to Wednesday. I don't have too many announcements, so I'll keep this short. The first one is that you do have daily quizzes out now. Every time I post a lecture video, you'll have a quiz on Canvas that you can take. Should be pretty quick, should take no more than 5 minutes. You can always access your notes, so it should be pretty straightforward. And these quizzes are a good way to checkpoint your progress throughout the class, so I really recommend you take them before you watch that day's video. And the quiz is going to cover the content from the last couple of weeks. The other announcement is that your Project Zero is due tonight, and I want to make sure you know how to submit this project correctly. Hopefully you've already read through all the project specification, you know how to run the test scripts. That's something I demonstrate to you in the project briefing video. And there are some detailed submission instructions down here when you click on the project submission instructions link. The short summary is that I'd like you to zip up the project folder and then upload that onto Canvas, where you'll find an assignment called Project Zero. And to be clear, when you zip up this folder, I want you to zip up the project folder itself, not the selected all version of the contents of the folder or a folder containing the project folder. So let me give you an example. Here on my folder, I have a project CSC 143 project 0 folder. Inside here, you see my source, you see my Git directory. If you'd like to get Git credit, please make sure this is available. And your filled out README. This is a text file. You can open it in a text editor. Make sure you fill this out, by the way. And once you're done setting that stuff up, I want you to go back up and then zip the folder of the project. So right click, and then in Windows, you can do send to compressed zip folder. In Mac, it's something similar, also in the right click menu. I use 7-zip, which I really recommend. It does something like add to archive. And once you do that, you send to zip. It creates a zip file that contains that folder, such that when I open that zip file, the first thing I see is the zip folder itself, because I'm zipping the folder. A lot of submissions I've gotten in the past tend to be something like one level up, where somebody zips that folder instead. And then it's kind of annoying because then I have to go open the project within that folder. Another thing I see a lot is zipping of the files inside rather than the folder itself. This will cause me to have to create a separate folder to create that project in and move the files inside that folder, so then I can actually grade it. So it would be really great if you could just zip the project folder itself and nothing else. It's okay if you mess this up. I'll try and give you comments on your project submission if you do, so that in the future you can correct this and give me the right zip files. Okay, that's all I've got. Today's lecture is going to cover equals, polymorphism, and generics. 3 pretty interesting topics, I think, that are really core to the fundamentals of object-oriented programming, especially here in Java, which uses a global equals method that's available from the top-level object that you are obligated to override as a developer whenever you define a custom class. Okay, enjoy the show. Hello again. Welcome back to another video lecture for CSC 143. In today's video, we're going to be covering the equals method, polymorphism, casting, and generics. Before we dive into all that, I want to briefly review our discussion last time about how classes can be thought of as containers of state. A class in Java is a blueprint for an object instance. Anytime I construct an instance of a class, it's going to be reflected by the properties contained within that class, which compose its state. Classes are also going to contain methods, which are functions attached to that class that manipulate the properties of that instance. For example, let's suppose I had a shape class and a circle class that inherited from shape. The circle could have a setRadius method that changed the radius property of the circle, where the circle's state is thought of as whatever radius it's currently sized at. Classes do have a special kind of function called a constructor, which is a method we use for initializing the class instance. And in Java, we're always going to use the new keyword prior to calling the constructor to indicate to Java that we would like to build a brand new instance in memory. Static methods are a special kind of method that's not actually attached to the instance, but instead the class namespace. We've briefly talked about static methods when we went over public static void main, but I want to make that explicit in today's discussion. Let's take a look at a.java. This public class A isn't too complicated. It just has an int I inside and a basic constructor that takes a single argument that assigns that I value, as well as a getter method that returns the I. I'll also provide a print method here that simply prints out the letter A and also calls a.staticPrint. Take a look at this definition for A's static print method. The method's called static print, it's a type void, but this time I've placed the static keyword in front of the return type and the name of the method. By nature of this method being a static method, what we'll see is that we can invoke the method upon the name of the class rather than an instance of the class. Let's take a look at this main method here. I initialize an A instance called foo with the value of 5, and I call foo.print, which I should expect to print out A as well as call static print here. Then down here, I refer to the static print method on the A class definition. This is only possible because static print is a static method, meaning it's attached to the definition of the class, not an instance of the class. So instead of saying foo.staticprint, I'm just doing A, which is the name of the class, .staticprint. One little fun fact about Java is that you can actually still invoke static methods on instances of the class. So even though static print is called a static method, we can still invoke it upon foo, which is an instance of A. Of course, IntelliJ is actually going to complain. It's going to tell me static member scratch.a.staticprint is accessed via instance reference, whereas instead I could access a.staticprint via the class A reference, just by removing foo and replacing it with A, or even removing A entirely because I happen to be within the definition of A already. Below, in these couple of lines here, I've got some method calls to some native object methods that we'll talk about very soon. Let's go ahead and run this main method just to see what comes out. I get A, static A, static A, and static A, which is what I expected. Let's head back to the README. Just like how classes are blueprints for objects, an interface is like a blueprint for a class. Interfaces declare abstract methods that don't provide implementation. Instead, interfaces are going to obligate classes that implement that interface to provide the concrete implementation. Java is going to treat object variables as references, which internally are actually just pointers to instances in memory. Remember our big discussion on how copying values is quite expensive as the size of the value grows, but Java is also a pass-by-value language, which means every argument that we pass in and every return value that we receive on the way out is actually copied. And the only way that really scales is if you do everything by pointer. As references are internally pointers, and pointers are plain integers, copying references is pretty cheap. A big discussion last time was, of course, about inheritance, one of the 3 pillars of object-oriented programming, and there was this idea that children classes can inherit things from parent classes. They inherit methods and properties that are protected and public. Children classes can also override parent method definitions. We can use the @override decorator to introduce a compile time check and let the JavaC compiler know that a method definition is meant to override a parent or interface declaration. If we had made a typo in our function call, our function definition, then the JavaC compiler would complain that the function's not overriding anything. One more thing, child classes can still invoke parent methods if needed by using the super keyword. And this is the same thing you'll have to do inside the child class's constructor to invoke the parent class constructor. Now that we know about how inheritance works, let's talk about some native object methods. All classes in Java inherit from object, the top-level Java class. Let's take a look at the official Oracle docs for more information. Class object is the root of the class hierarchy. Every class has object as a superclass. All objects, including arrays, implement the methods of this class. If we take a look around an object, we're going to see some methods like clone, finalize, getClass, hashcode, toString, which we're familiar with already, that is going to exist in all classes by nature of all classes inheriting from object. So why did the Java designers decide that all classes needed to have certain methods attached to them? Well, the Java language designers decided that it would be practically useful if all engineers knew that, for example, toString could be used to convert a class instance to a string representation, and equals was the method that you would call in order to compare a class instance to another. So by nature of defining all these functions inside the object class and all other child classes that are defined receiving these methods, those child classes, are going to always have these methods available to them. That being said, these method definitions aren't particularly useful right out of the box, which we'll talk about very soon. The methods that we do care about are going to be toString, which returns the string representation of the class as decided by the developer, equals, which is going to compare two objects by their internal state, a sort of value equality rather than a physical equality. Sometimes I like to call this semantic equality. And hashcode, which is going to return the hash of an instance for use in fast lookup tables. And we'll talk more about that when we learn about hash maps in a couple of weeks. Let's go back to a.java and see what happens when we actually invoke these inherited top-level object methods and see what we get. Okay, on line 31, I create a new a with 5 inside. I call toString. Then I try to use the double equals operator to compare bar with foo, the a we defined up here, which also has 5 inside. Then I try to use bar.equals foo, and finally bar.hashcode. And here's what we get on the way out. toString gives us scratch.a at 7a79be86. The next two lines give us false and false, despite the fact that both a's contain 5 inside. And the last one gives us this big number down here. So what's actually happening? Why aren't these output results particularly useful to us? Well, toString, equals, and hashcode, these are all methods that the top-level object is going to give us for free, so to speak. Remember that the parent class can provide method definitions, and child classes that inherit from those parents automatically inherit those method definitions. But the native object implementation of these methods isn't particularly meaningful. The native object implementation cannot know in advance what child classes will exist, and its implementation isn't going to be smart enough to figure out how to actually convert instances to strings in meaningful ways or define equality in a meaningful way. So what the base class object actually does is it gives us some primitive, uninteresting implementation that we can just use, but as developers, we are more or less expected to override on our own. For example, let's take a look at this equals method. It's a little odd that foo and bar are not equals to each other by value because, of course, they both have a inside. So what is the equals actually doing? Well, if we press the control key on our keyboard and click on the definition, we can dive into object's definition of equals, and we see that, oops, it actually just does a reference equality. So again, Java's object equals and all the other methods that it provides us aren't particularly well defined. They will do something that resembles a stub implementation, but isn't sophisticated enough to actually apply automatically to whatever your class definition is. We've talked about reference equality and how it is going to try to perform physical equality between the two objects, which quite literally requires foo to be bar. So if I have two separate live instances, like foo on 24 and bar on line 31, those two instances are going to live in two different places in memory, and these two things are not going to be equal to each other. Sort of fun fact in Java, the toString implementation is going to print out roughly the memory address of the actual instance. I think if we dive into toString, we'll get some more details. Actually, no, I guess I'm wrong. Well, I'm glad I checked this out. If you control click on toString, you see that it's going to get you the name of the class, which in this case is scratch.a, the @ symbol, and then integer .2 hex string of the hash code. We'll talk about hash code when we learn about hash maps in a couple of weeks, but it looks like it's going to convert that into a hexadecimal representation of this big number down here. Oh, I learned something new today. Awesome. Okay, So now that we've learned that these object level method implementations aren't particularly useful to us, and the Java engineers decided that it was upon the developer to override them to make meaning out of those methods, let's talk about equals. Recall that double equals, the operator, is going to compare two objects by memory address, and two primitive types by value. We saw how foo and bar didn't equal each other despite the fact that they both had file inside, because they were two separate objects in memory. However, when it comes to primitive types, we can use the double equals operator to compare two different primitive values, because for primitive types, it's just going to do it byte by byte. So the number 5 in one place is going to be double equals the number 5 in a different place. The dot equals method, public boolean equals, is going to extend this notion of value equality or semantic equality to classes so that you can compare different instances that have the same internal state but different references. By defining this equals method here, I can have a method that says foo does equal bar because they both have the number 5 inside, and that 5 is the internal state of the two objects. One more thing before we check out some examples, check out this argument signature right here. We have an equals method, there should be a dot there, equals method that returns a boolean type and is public, and the only argument is type object. The clever thing about having a type object inside your argument type is that it allows anything to be passed in as an argument. Remember that all classes inherit from object. Polymorphism is going to enable us to represent any class reference as the object reference, so we can actually pass in any type we want here. Of course, it doesn't necessarily make sense that this type can be equal to any type. We should have to do a comparison to make sure that the type we're comparing against, the argument, is going to be equal in class to the same class that we have right now. Let's take a look at some examples with point and point3d. Point.java is a relatively simple class that contains simply two properties, x and y, that are just integers, and a constructor that assigns those two values. The toString implementation simply returns x and y in coordinates in string form. I think a pretty reasonable implementation of equals for point would be just to compare the points by value. I should expect that the x equals the point that I'm passing in, and the y equals the same y as the point I'm passing in. Let's take a look at my equals implementation here. Remember that my method signature tells me that the argument has to be an object type. I'll put this @override decorator here to tell the compiler that I'm intending to override a method. I'm going to start out with a null check. If the object being passed in is actually a null reference, return false. This null check is pretty important because it is essentially an escape hatch, an early exit that lets me quickly identify objects that don't actually exist, that are null, and return false. So I don't have to do any extra comparison work. We know for a fact that if we're inside the body of this equals method, then the instance that we're running on is not null because I can't invoke equals on a null instance. So therefore, if the object is null, I know I'm not null, I can return false right away. Similarly, I can use the double equals operator against the this keyword to retrieve a reference to myself and compare it physical equality-wise to the reference being passed in. Double equals is simply going to ask whether the underlying memory address stored in this is equal to the underlying memory address stored in O, and if that's the case, I know these two objects are physically the same, and I can return true right away. Now let's go down here and take a look at these two examples. I've commented out this first block, but let's talk about the second block first. I'm asking if the object being passed in is an instance of point. Instance of is actually a keyword in this circumstance. If that's not the case, go ahead and return false. Remember that the method signature of equals required that I take in an object type as my argument. I'm not guaranteed that object type is actually a point, so I need to do a runtime check to validate that the object being passed in is an instance of that point. If that's not the case, of course, I can return false. Finally, when I've reached this point on line 34, I know that the object type is a point type because I passed this guard statement up here. So I can cast the object to a point by putting the name of the class I want to cast to in parentheses and next to the reference. That's going to give me this reference other, which of course points to the same thing as O, but now by nature of this reference being a point type, I can refer to the properties on that point. I'll go ahead and do the value-wise comparison of the x and the y fields and return the outcome of that result. Okay, so not too hard. We've got some early exits that are important to us, especially when it comes to classes of higher complexity. We've got a runtime check to validate that the object being passed in is a point type. We do a cast to turn that reference into a point reference, and then we do a value-wise equality upon all the fields inside that other object against our object. Now let's extend this notion with inheritance. Let's take a look at point3d. Point3d is going to be a class that extends point. I'm going to inherit the fields x and y because those are public integer fields, but I'm also going to define a new field public int z. I'll define a constructor with 3 arguments, x, y, and z. I'll call the superconstructor with x and y, and then I'll assign the current z field with the z being passed in. I'll also override the Tostring method to give me 3 coordinates instead of 2, x, y, and z. Alright, now let's take a look at the equals implementation for point3d. Once again, my method signature has to be the same. I'll put this @override decorator to let Java-C know that I'm trying to override the equals implementation provided by my parent classes, including point and object. Once again, I'm going to include these guard statements. If O double equals null, then I can return false, knowing that my current instance is definitely not null. If O double equals this, then I know that these 2 object instances are physically the same and I can return true right away. Down here, I'm going to do another runtime check, but this time I'm going to refer to point3d. If the object O is not a point3d, it's not an instance of point3d, I'm going to return false right away. Otherwise, I will defer equality to the parent class by calling super.equals_o, and then I'll compare the z field of the point3d inside the argument O. This is essentially an inline cast. In this expression, I'm casting the reference O, which is an object reference, to a point3d reference, which is going to let me refer to the z property. So in general, equals is going to be implemented this way. We're going to do that null check to save us some time. If the object being passed in is null, we'll do the self-equality check, do an early exit if possible. We'll check to see if the types are equal. This time we've been using instance of. We'll talk about getClass in a moment. If this is a child class, we'll call the parent equality. And then finally, we'll do a value-wise equality for all of our internal fields. Let's go visit the test case to see how it works. Okay, starting out with point test, I've got 2 points, one that's 0, 0, and one that's 5, 4. I can assert that the first point, 0, 0, a, is going to be equal to itself, a.equals a. I can assert false that a equals b, because of course these 2 x and y coordinates don't line up. If I modify b's internal properties such that it also exists at 0, 0, then I can call assert equals a and b and get the assertion to come back true. Assert equals is just a shorthand way of saying a.equals b, and it also works symmetrically. B is going to equal a, because it shouldn't matter which way I refer to equality in this case. The double equals operator, though, is still always going to perform that reference equality, so this is still going to be a false statement. Now let's extend this to point3d. Let's define a point A at the origin again at 0, 0, a point 3db at 1, 2, 3, and a point 3dc at 9, 8, 7. I assert that b equals itself. Okay, self-equality, that check works. Then I assert that a is not going to equal b, because of course a is at 0, 0, and b is at 1, 2, and 3. Now let's ask what happens if I update b's x and y fields to 0, 0. Note that this does not update b's 3 field, which is assigned to z. So I update x and y to 0, 0, like matching point A, but I do not update the z field, which is currently set to 3. And what you might be surprised to find is that A is still going to be equal to B. Why is that the case? Well, A is a point type. On point, I define an equals method, and inside points equals definition, I do a value-wise comparison of the fields x and y. In this case, B is indeed a point because of polymorphism. B is a point 3D, which inherits from point. And B's x and y fields are going to also be 0, 0, because I assign them to be that way. So despite the fact that B has a z field that is 3, and A has no z field at all, I'm actually going to get true on the way out of this call to A.equals B. So that might seem kind of weird to you, right? Point 3D has an additional field that is set to 3 in the z direction that point doesn't even have at all. And yet, point A says point B looks equal to me as well, because x and y fields line up to be the same. This is the case because we're currently using the instance of keyword in our equals. Let's go take a look at that equals implementation again. Control click to go into the definition. Down here on line 30, I ask if the argument being passed in is an instance of point. And what instance of is going to do is it's going to permit references to point as well as references to any child of point to pass this check. So whether O is a point or a point 3D, it's going to pass, and it's not going to return false. It's going to continue execution. So when I pass in that point 3D in, that point 3D is going to pass the guard statement. It's going to be cast to a point, which is okay because point 3Ds are points. And then the only comparison that I do is that of the x field and the y field. I don't compare the z field here because point is not aware that the z field actually exists. So really what's happening is this guard statement, the instance of keyword, is too loose. It's permitting the point 3D to pass through because all point 3Ds are by nature point. Going back to point test. So here's the effect. When we use instance of in our equals, parents are allowed to equal children because children are cast up to the parent type. Only then the parents portion gets compared. However, we lose a rather important property, which is symmetry. Check this out. B.equals A is actually false. Why is that the case? Well, B is a point 3D. B has a z field that's assigned to 3. When I invoke equals upon B, I'm really invoking point 3D's equals definition. Let's dive in and take a look at what that looks like. In point 3D's equal definition, once again, I use instance of, but this time, I do an instance of point 3D. Remember that instance of is going to permit class references that are equal to the class on the right-hand side, as well as any of their children, to pass through the check. However, because I'm passing in a point instance and not a point 3D instance, point is a parent of point 3D, not a child of point 3D. Not all points are point 3Ds. Therefore, this check is going to fail, and I'm going to return false. So that's a really interesting side effect of using instance of. I lose symmetry. A equals B, but B does not equal A. That's a really interesting side effect. And whether or not you want this behavior in your program is actually up to you as the developer. Let's suppose for a moment that you're writing a graphics program. And in your graphics program, you have both points and point 3Ds. To simplify your engineering effort, you'd like to make it so that points can be equal to point 3D. In this case, sure, that can be done. You can allow point 3 instances to pass through equals and compare by the XY coordinates. However, there could be a point of confusion where you try to compare it the other way around, where the point 3D tries to be compared to the point. And the z property of the point 3D prevents the point from being compared against it. The alternative to using instance of is the getClass method, which can be used to explicitly require that two objects being compared have the same strict class and not just the same class within the same hierarchy. You're going to get a reading this week with more detail on how the difference between getClass and instance of will behave, but let's actually just go into a live demo. Let's go back to point and see what happens when we replace this guard statement, which uses the instance of keyword, with this guard statement that uses the getClass method. GetClass is another one of those methods that the object class is going to automatically provide to all of its child classes. And what it does is it's going to go return a reference to the actual class definition. So this is a bit of meta programming going on here. When we define this class, and this class acts as a blueprint for all created instances, this class actually does live in memory, the class definition I mean. And what getClass is going to do is it's going to go retrieve the reference to the actual class definition. So one way we can enforce that the current instance and the argument instance are the exact same class match, strict equality in that case, we can use the getClass method, which should give us a reference to the actual class definition. If it's the case they're not equal, then we go ahead and return false. You can read more about this on the official Java object documentation, where you can check out this getClass method that returns a class type, which if we open is part of java.lang, so it's actually like a language level feature. And that's going to give us the runtime class of the object. Because getClass is going to only return a strict instance, there's only one definition of point here. We can use the double equals operator to make sure that the class on the left is the same as the class on the right. Okay, now that we've done that, let's go visit our test again and see what happens. Let's try running this test. And what we get is an assertion failure, where suddenly A no longer equals B. That's the case because A is a point and B is a point 3D. And now A, thanks to the getClass call, is going to require that B has the exact same class, regardless of where it belongs in the hierarchy. If we look at B.equals A though, let's go ahead and fix that out too by going to point 3D's definition, so that it calls getClass instead of instance of. If we try running this test again, we should expect that both assertions fail. Actually, I think I need to comment out this first assertion, given that it's never going to reach the second one. Interesting. B equals A. Let's go fix that. Why is that the case? If this.getClass is O.getClass, return false. So B is definitely a point 3D type. A is definitely an object type. Well, I'm not actually sure why that's failing. Let's hop into the debugger and find out. Ah, this is an assert false, not an assert true. That's the reason why. Huh. Okay, so this test does indeed pass. But if we change this to an assert true, of course it would fail. So there's two ways that we can go about writing equals. We can either treat child classes as being the same as the parent and use the parent's properties to ask if the child's properties are the same, and if so, consider them equal, at the cost of symmetry. Because all point 3Ds are points, we can compare points to point 3Ds, but not all points are point 3Ds, so we can't necessarily compare a point 3D to a point. Whether or not you want this behavior in your program is again up to you. You may either want strict equality, which is a bit more consistent but less flexible, or have this cross-class equality, which is more flexible but of course also less consistent. You might be wondering why we wouldn't always just use getClass and want to apply strict equality. And the reason is because of something called the Liskov substitution principle, which you're going to get to read about pretty soon. The Liskov substitution principle more or less says that child classes should be able to substitute parent classes wherever a parent class is expected, and the substitution should be completely transparent to the client who is requesting those class instances. So if our equals method is inherently asymmetric, then we violate that principle because our child classes will behave differently in the place of where parent classes are expected. At the same time though, losing symmetry of equality is kind of a weird thing, right? Not being able to say one equals the other in a particular direction is kind of strange, especially if you have two references that are both top-level references or the same reference. What I mean by that is if I rename this reference to point, suddenly it's a lot more opaque what's going on here. It's weird that both references are point types, but one is equal to the other, but not the other way around. So this is one of those trade-offs you'll have to make as the engineer and decide in your program specification how you would like this to behave. So in summary, instance of will permit parent classes to equal child classes, but violates that symmetry of equality, whereas comparing the return values of getClass is only going to allow objects to be equal if their classes are strictly equal, preserving symmetry of equality, but violating the Liskov substitution principle, which you'll get to read about pretty soon. Now on the topic of how we reference the actual underlying instance, I want to raise a question, which is, does the type of the reference of an object instance change which implementation of equals is called? The answer is no, but let's think about this. Let's go visit that test again. And ask ourselves, does changing B's reference of a type of point3D on the left-hand side to a point cause points equal to run instead? Let's start out with the unchanged version of the test and just run it to validate that it works, which it doesn't because we need to go fix our definition. Let's go back to point and switch it back to using instance of. Same thing goes for point3D. Now let's try running this test again. Hopefully it should pass. Great. Okay, so the question I raised to you is, does the type on the left-hand side here, the type of the actual reference, regardless of what's on the right-hand side, does that affect the method that gets called? Well, let's try it out. If I replace point3D as the type for B to be a point, which is valid thanks to polymorphism and the fact that all point3Ds are points, is b.equals going to invoke points.equals instead of point3Ds equals? Well, if we run the test, it all passes, so it seems on the surface level that's not the case, but let's dive into further detail. Remember down here, we expect A to equal B because A is a point and B is a point3D underneath. And we also said that parent classes could equal child classes using the instance of keyword. But we said that because B is a point3D type and A is a point type, B should not allow equality with A because not all points are point3Ds. When we run B's instance of, we are comparing against, we are comparing a point against a point3D type. And it looks like IntelliJ itself is actually not quite smart enough to figure this out. Let me show you this actually by going into the debugger. Let's put a breakpoint here and step through this equals call and see exactly what happens. Whoops, need to hit debugging mode. Okay. So here we see that B is most certainly a point3D because it's got 3 values in the toString implementation, and A is a point2D. It's only got 2 values. Remember, this is the case even though B is referenced as a point on the left, and it's a reference as a point on the right, as a point3D on the right side here. By the way, one kind of clever thing about the IntelliJ debugger is it's going to try and represent the string values of the objects being examined in line with your code. So it's actually calling toString here to get these underlying string representations. And if you think even more ahead of what IntelliJ is doing, you can already realize that Java does the smart thing and it tries to run, or it does run, the most specific implementation available. So even though point has a toString method that returns the first 2 points, x and y, and point3D has a toString method that returns 3 points, x, y, and z, referencing point B as a point type and not a point3D type does not prevent the toString call from running the point3D's toString. So indeed, Java is picking correctly. It is going to go find the most specific implementation available for the class. Anyway, now that we're past at this breakpoint, let's go open the debugging window again. and step inside to this equals call. We'll click on step in. It's going to ask me which method to go into. Let's go to equals. And when we scroll up, we see that now we're inside the body of point3d. Now let's try and walk through what's happening here. I step over, I step over, I step over, and I see that the object we're passing in, which was that point A, is being compared against the point 3D here. This is the case even though back up when I called point dot equals, b dot equals, and b was a point type we declared in line 33, Java is going to go run the most specific implementation available, which is the equals method on point 3D. Okay. So hopefully that makes things clear for you, and we're going to talk about this when we go over polymorphism formally in this next section here. But always remember, Java is not going to care what type you refer to the underlying instance with. It does care what the underlying type is, and it's going to go find the most specific implementation it can find. Now it's time we go into that into more detail. Polymorphism is the second pillar of object-oriented programming, and quite literally it means the condition of existing in several forms. In object-oriented programming, polymorphism is this notion that a single interface can be fulfilled by different unique types, or classes. We've already seen an example of that. Different classes can implement the same interface. We've seen interfaces like comparable, which is implemented by big integer and string. We've seen interfaces like iterable, which is implemented by list, map, tree, and several other structures that we'll learn throughout this class. A class can implement any number of interfaces. Interfaces are mix and match. And child classes naturally supply the same interface as their parents. Remember that child classes automatically receive the public and protected methods of the parents. So when examining a child class instance, we get all the same public methods that the parent method already exposes. So this notion that a class fulfills a given interface allows us to treat instances as being that interface. Classes and their parents form an is-a relationship. Classes and their interfaces form an is-a relationship. We've already seen this in action in some of the previous examples. We saw how point3d is a point, so I'm allowed to assign a point3d where a point belongs. We've seen how shape is an interface, and I can assign a circle to be a shape, even though shape itself doesn't have concrete method definitions. Shape, remember, is an interface. Let's take a look at that in explicit detail with some of these Java files. Shape.java. In this interface, I'm going to have an area method that returns a double, and a getLocation method, which is new to us, that returns a point, the same point definition that we just went over, the x and y. Let's go look at circle. Circle implements shape, which obligates circle to provide the methods that are declared in shape, those two methods being getLocation and area. I've used the @override decorator to let Java know that these methods are expected to override something. I've got a basic 2-argument constructor that simply assigns the radius and the location, and I've implemented my area method such that it computes pi r squared. I've also got an implementation of equals down here in case you want to take a look. Now let's go look at rectangle and see what's going on in this class. Once again, rectangle implements shape, which obligates rectangle to have a getLocation and an area method attached. I've got a constructor with 3 arguments, an int width, height, and point location. I've got some unique methods like rotate 90 degrees, which simply swaps the width and the height, a getWidth method and a getHeight method, and of course my getLocation and area methods, which are required by nature of rectangle implementing the shape interface. However, we do expect that rectangle's definition of area is different from circle's definition of area. Of course, the area of a circle is pi r squared, the area of a rectangle is width times height. So the shape itself has no say in how the actual area gets implemented. The shape simply says, if you would like to be a shape, you better tell me how to actually provide the area. Let's look at one more class, the square class. And this time square is going to extend rectangle. By nature of square extending rectangle, square implicitly implements the shape interface. Remember that rectangle implements shape, which therefore has the area and the getLocation methods. Square extends rectangle, and square is going to automatically inherit the public and protected methods of rectangle, which means that square automatically inherits area and getLocation for free. So the nice thing about this definition is all I have to do is build a constructor, which I'm going to use this clever repeat of the single argument side to make my width and height the same for my rectangle, construct the rectangle side with the same width and height, and otherwise do nothing else inside this class, because the square class is going to get all the obligations it's required to fulfill for free by extending the rectangle. Now let's go take a look at the test. We'll start out with a single point definition called origin, new point 0, 0. We'll verify that we're still using instance of, so I'm allowed to compare origin to point 3D. Let's go ahead and actually just run all the tests in this file to make sure we're still good. Great. Then we've got a rectangle test here. Rectangle R is new rectangle with width 5, height 10, and at the origin, and I expect the area to be 50. Let's go a little bit more complicated. Rectangle R has a width of 10, width of 5, height of 10. Rectangle Q also has a width of 5 and height of 10. But this time, its point 3D is going to be actually a new point 3D and not this point 2D, which is the origin we declared at the very top. In this comment here, I say rectangle equality only cares about the equality of its properties. Implementation of point is responsible for its point equality. So just by looking at these rectangle definitions on lines 38 and 39, I know the width and the height are the same. The question is origin and this new point 3D declaration the same? And in this case, rectangle is going to defer equality to the origin, or defer equality to the point definition, I mean. In the case of origin, well, origin was a point 2D, and we said that point 2Ds were allowed to be equal to point 3Ds. So I would expect these two rectangles to be fully identical. All of their internal state properties are technically dot equals each other. Let's go take a look at the equals implementation and see how that works. I've got the basic guard statements, the null check, the self-equality check, and the instance of check. Then down here, I compare all the internal values of the rectangle. Width has to be equal, height has to be equal. I can do both of those via reference equality because they're just primitive types. And then I do location dot equals, the get location of the argument. The great thing about being able to call equals on any object is you can essentially defer equality verification to that object. Rectangle itself doesn't have to know how point is implemented and how it's providing the equality of two different points. All it has to do is call this abstract method that's, well, not abstract, it's abstracting away the act of comparing 2 points and treat it as if it was just another value that has to be compared within the state of the two rectangles. Let's keep going. Now let's check out this example. Squares are rectangles. Squares fulfill the same interface that rectangles already supply, so I'm allowed to assign a square on the right to a rectangle on the left. When I call the area method, well, the area method is actually implemented by rectangle. So square doesn't have to do any extra work. It's just going to do width times height, which of course is 5 times 5, and gets us to 25. What about this toString call down here? R.toString. Well, R is a rectangle type. Rectangle has a toString, but if we look at square's definition, we'll actually find that square has overridden toString to say square instead of rectangle. So does that mean I'm going to get rectangle 5 times 5 because I have a rectangle on the left? And of course the answer is no. Just like how the equals method is going to call the most specific implementation, the toString method is going to behave the same way. Java is going to be very consistent about this. Regardless of how you view the type of a reference, it's always the underlying type of the instance that matters. And Java is going to go find the most specific implementation that's available for that underlying type, regardless of how we look at it, how we look at that type based on the type of the reference. So here, this toString call, despite it being on a rectangle, it's going to go invoke square's toString, because square is the actual type that the reference is pointing to. All right, now let's go even deeper. Here I've defined 3 shapes, R, S, and C. R is a rectangle with has 2, 4 at the origin. Square has sides that are 3 by 3 at the origin, and circle has a radius of 10 at the origin. Rectangle, square, and circle all implement the shape interface. All shape expects is that it provides a getLocation and an area method. So I'm allowed to assign the instance on the right to the interface on the left because the instance on the right fulfills the expectations of the instance on the left. This is despite the fact that the interface itself cannot be directly constructed. Now, I've put all these lines here as a way to emphasize that you might have a really, really big program. It may not be immediately obvious what the type for the interface is being fulfilled by. If I scroll down past here, well, I've reached another big block of code. I may not necessarily know what R, S, and C are. If I'm just told they're shape types, I may not realize that they're rectangle, square, and circle respectively. But that doesn't matter. Shape exposes the methods provided by the shape interface. Therefore, we can safely call those methods despite not knowing the actual implementation of the underlying shape class. So I can say r.area. I know area is a method that belongs on shapes. I don't know necessarily what the shape is. It could be a very complicated program. That doesn't stop me from calling the area method on these 3 shape types. Same thing goes with getLocation. I can invoke getLocation on the shape type because I know all shapes, regardless of who chooses to implement them, will have a getLocation method available. Okay, let's make it a little bit more complicated by throwing casting into the mix. Before we show you casting though, let's reiterate this big idea. When a child is substituted for a parent, the child's implementation gets used at runtime. Clients using parent classes do not care about the underlying implementation, only the public interface. The underlying implementation of an interface can be extended by children classes, made more specific by the child class overriding the parent methods. This is shown with that toString method that was re-implemented by the square class. Square replaced rectangle's toString and made it more specific by saying I am a square, not just I am a rectangle. And by doing so, calling toString on square instances is going to invoke square's toString and not rectangle's toString. Then when we have those child classes, they can be referenced as the parent class without knowledge of the child class. Let's see. It can be referenced as the parent class without knowledge of the child class. Underlying implementation of an interface can be extended by children classes, made more specific by the child class providing parent methods, and referenced as the parent class without knowledge of the child class. Yes, the without knowledge part here is essentially saying you can do it without knowing that it's being done. And this is that case with that rectangle, square, and circle, where I use the shape without necessarily knowing the underlying shapes. That, of course, is very much abstraction. I don't know the underlying complexity. All I'm exposed is that public interface. Now let's try and make things a little bit more complicated with casting. Casting is a way of treating one reference type to act as another type. For example, I can cast the square into being a shape. We actually saw casting in action with the point and point3D implementations of equals. Let's go take a look at that again by visiting point3D. And if we go to the bottom of the equals definition for point3D, we see that in order to retrieve the z field of the argument instance, I have to cast it to a point3D first. Casting is performed by declaring the type and putting it in parentheses. And it essentially tells Java, look, I know what I'm doing. This is actually a point3D underneath, so give me access to the fields of point3D so I can access them for the sake of comparison. If I remove this cast to point3D, Java's not going to let me reference this z field. It cannot resolve symbol z, because of course, O is still a reference to an object. I have to cast it, that reference type, to be a point3D reference so that I can look up the z field on that reference. So the syntax of casting is pretty straightforward. Just put it in parentheses. But there are some rules around casting, and around what works and what doesn't. It's always safe to cast up the class hierarchy. Squares are rectangles. Rectangles are shapes. I can always cast up. It is dangerous to cast down the class hierarchy. Not all shapes are rectangles. Not all rectangles are squares. To cast a reference, we specify the desired reference type in parentheses next to the object. For example, square square is new square at 5 origin. Shape is square. This is an example of an implicit cast. We could have said shape next to square here, but we don't have to because Java is going to recognize that I'm assigning square to be a shape type. Always safe to cast up because the child class is always going to fulfill the interface of the parent or any of the interfaces that are being implemented. However, shape may not be a rectangle, and I should do an instance of check to determine if the instance is actually a class or a child that I'm trying to target. Well, what do I mean by that? Well, let's say there's a big whole bunch of code that's going on between this line 126 that made the shape be a square and this line 131. It's entirely possible that this shape reference has changed over time. Could it be a circle? Can we try making it a circle? Well, if I forcibly cast it to a circle and try to put it inside a circle reference, what I'm actually going to get is a type error. We saw this type error actually in our review of primitive and reference types. Remember how I told you Java's going to figure out sometimes where two types are incompatible? Well, here's one of those circumstances where it's kind of ambiguous. I know some shapes are circles, but also some shapes are rectangles and some shapes are squares. So Java doesn't know at runtime what this type could be, so it's going to permit me to do this. The compiler is not going to stop me, but I will get an error if this is an invalid cast. If this shape is actually a square underneath, trying to force it to be a circle will throw an exception. The way we get around that is by using the instance of keyword. We can validate that the shape we're trying to cast is indeed the class we're trying to target. If shape is actually a circle, then we're guaranteed inside the body of the if statement that shape is indeed a type of circle, and I'm allowed to perform this cast with safety. So, just follow the tool rules. It's always safe to cast up. It's dangerous to cast down. And I think this is pretty easy to remember based on just how the interfaces are fulfilled. The more specific classes, the deeper you go in the class hierarchy, the more complex and specific those method implementations will be. And those child classes may also expose additional methods that the parents don't have. But we also know those child classes will always have the same interface as what the parent has, if not more, so it's always safe to cast up, but we can't necessarily go the other way. We don't always know that a shape is a circle, a rectangle, or a square. So we will need to do this sort of check to make it safe. Now I'd like to turn to a different language feature that enables class reuse called generics. Generics are a powerful language feature that allow you to reuse the same class with different variable types inside. Let's start out with an example called parint. Inside the class parint, I have two integers left and right. I have a constructor that accepts integers and assigns them to the integer values in our internal fields here. And I also have an equals method that does the necessary checks and then performs the cast to ask if the left field is equal to the right field that's being passed in. So this pair class is nothing particularly special. It's really just a container for two items, a pair of items. Sometimes we see these items as relating to one another. Sometimes we see them as key value pairs, a relation between the left field and the right field. We can think of parint as just a reusable container for two integers. What we'll observe with parint is that the integer portion of parint, the fact that we're using integers, isn't particularly meaningful. We could have replaced those integer fields with string fields, and then we'd have a class that was a pair of strings. Or maybe we wanted to use big integers, and we have a class that was a pair of big integers. Going around defining a new class for every single type that we'd like to put inside of a pair isn't really sustainable. We'd have to essentially enumerate the entire universe of types to get all the different pair variations of those class definitions. Generics are useful to us when your class contains a type, but does not depend on its interface. We're going to make it so the type is provided by clients or users of the class itself. Here's how that's going to look. The syntax for declaring a generic type depends on where the type itself is going to be scoped. Whenever you see these angle brackets, expect generics. We've briefly seen angle brackets in a couple of examples where I've talked about the array list and how that's an ever-expanding array that takes a generic type, such that all the elements inside that array list are going to be references to that type. We've seen the hash map and the hash set and how those will map one type to another or be a bag of items of a specific type, respectively. Let's do that to our own custom classes. To declare a generic class variable, we declare the generic type next to the class name. For example, if I am going to have a generic class A that has a generic type T, I put inside the angle brackets, by convention, a letter to indicate that there is a generic type available here. To declare a generic class variable for a child class, that is, a class that's going to extend an already generic class, we can declare generic types next to the class name and the parent. For example, we can have a child class that's itself generic, which is going to involve extending an already generic class. So here, the class B is going to have two generic types, T and V, which is also extending the class A that has a generic type T. And by nature of us reusing the letter T in these two locations, we're essentially telling Java that B's first generic type is going to match A's first generic type. Then when it comes to actually constructing an instance of a given class with a generic type, we're going to do so by specifying the type in angle brackets next to the type itself. So if I wanted to declare that class A as a reference, I'll declare A, put in angle brackets the type I'd like to declare, the name of the variable, don't forget that. Then when I call that constructor, I once again put in angle brackets the type next to the class name. We've also seen this shorthand of not having to define the type on the right-hand side, and this is available to us if Java can implicitly determine what the type of generic is going to belong in that location. So because this constructor is pretty obvious, and this type on the left is very much directly associated with the type on the right, we can save ourselves some typing and not have to write that in. I'll go ahead and put that back just for explicit reasons. To declare a static method which accepts or returns a generic, we can actually declare a generic in line with the method definition, and we do that before the return value. Remember the static field, or the static keyword? It indicates to Java that this class's property or method is going to be attached to the class definition and not an instance of the class. So my method, which is attached to some class, can be invoked directly on the class definition. However, because it's attached to the class, even if the class itself is generic, it's not going to have access to those generic types because there's no instance to access those types from. So if you would like to scope in some generic types onto the definition itself, you can do so by placing it before the return type of the method. This also works for non-static methods as well. If you have a generic class or even a non-generic class that would like to have generic methods, you can define a method that is inherently generic without necessarily requiring the parent to have a generic type available. This has some limited use cases, but it is necessary sometimes when you'd like to maybe define like a helper class that has a whole bucket of methods that do assorted things and need to accept different generic types that are scoped to just the methods themselves. So let's go from the pair int to a generic pair and see how that looks. Okay, I've defined my class pair. It's got an L and an R generic type. And once I define these generic types inside angle brackets next to my class definition, I'm allowed to use the generic types inside the body of my class as if I knew what those types were. So here on lines 11 and 12, I've declared an L left and an R right. Similarly, in my constructor, I'm allowed to use types L and R within the arguments of the constructor. Then I can go ahead and assign those values to my fields. Here I've got a function called getLeft. In particular, this example isn't really that interesting. I put in this array list here let's go ahead and get rid of it for a quick second, so we can simplify our definition. Here, my getLeft simply returns a type left, and it just returns the left field. I think I put that array list there to demonstrate to you what it meant to have a generic type scoped within a particular method, but let's put that back in a minute after I finish reviewing this class. Here I have a static method, createPair. This is just going to be a factory function that's going to enable me to build pairs just by a function call. But by nature of this function itself being static, the function is not going to have access to the generic types provided by an instance. Remember that when we construct a generic type, we declare during construction time what the generic types will be assigned to. But because createPair itself is a static type, I invoke createPair directly on the class definition itself, and I don't have an instance I can refer to that has those generic types defined. So what I'll have to do is define some generic types that are scoped to the method itself, which I do so before the return type of the method, and then I'm permitted to use those generic types inside the body of the method. So here I'm saying createPair is going to have two generic types, A and B. It's going to return a pair of A and B, and it's going to take two arguments, A left and B right. And it's simply going to call the constructor with A and B as the generic types being assigned. Finally, I've got my equals method. Equals method signature is always going to be the same because I do need to override objects equals, which has this particular method signature. I'll do the necessary precondition checks. Then I'll do the cast and refer to the left and the right side values. Let's go back up here and have a kind of silly discussion about what it would take to append on additional generic types to this particular getLeft method. GetLeft isn't really that interesting. I'm just showing you this for example reasons. Let's say for a moment that getLeft actually requires additional generic types to be defined for it, but the pair itself doesn't provide those types. Let's suppose for a moment in a weird way that I needed an array list here, and that array list could be of any type. Let's go ahead and say it's type T. Well, this type T doesn't necessarily have to be left and right, but I need to accept an array list of any type. So what I can do is I can define an additional type that is scoped to the method itself. Just like how we defined A and B down here in createPair with the static method, I can define new generic types that are scoped to the method itself. This needs to be a T. There we go. That's going to let me refer to this array list without losing context of what generic type is contained inside. It's also not going to require me to define that generic type up inside the definition of the pair class. So this is one way you can make your methods be generic on their own without obligating the class definition itself to be generic. Okay, so that is going to be our reusable pair. It's going to be two elements that are just contained inside a class. This class is essentially a container with those two things, but it's going to be reusable. We can use it with integers, we can use it with strings, we can even use it with mixed types, where we have a string on the left and an integer on the right, or vice versa. Let's take a look at how this is going to behave when we extend this class in pair triple, or triple. Let's go up to the top. Public class triple, LRT, is going to extend pair of L and R. Pair itself is generic. It has two generic types, L and R. And triple is going to declare its own types, L, R, and T. And by nature of L and R being the same letters as pairs L and R, triple is essentially saying my first two generic types will match the first two generic types of the pair. The T here will be pair's own unique third field. As you can imagine, triple is like pair, just with an additional field. I have a left, right, and third value constructor. I'll assign the left and right fields by calling the superconstructor, and then I'll assign the third field just directly inside the class definition. For this create triple method, this factory method that's also static, I do the same thing as I did inside the body of pair, where I define that create pair class. Sorry, the create pair factory method. I define my scoped generics A, B, and C within the body of the method, within the declaration of the method. Then I can refer to those generic types A, B, and C, and then return that triple on the way out. Once again, I've got an equals method. I do the necessary preconditions, null check, this check, require strict class equality for this one, call the super pair equivalence as necessary, and then compare the third field within the triple. Okay, so this isn't particularly complicated. The triple is just a natural extension of pair. One question you might have is, can we extend a version of pair that doesn't necessarily have a generic type attached, that already has a type defined for L and R? What I mean by that is, let's suppose we wanted to create the class that was triple integer, but we wanted to extend pair because it already had the functionality we wanted out of a pair container. However, pair itself is a generic type. Triple, does it need to be a generic type like pair is? And the answer to that is, it does not. I can define a triple int as its own class and extend a class that is generic, but go ahead and define the generic types at the top of my class definition. What that's going to give me is essentially a class that has a parent with fixed types, a not generic class, because I've already gone ahead and said that those types will be a certain type. So Java is pretty flexible about this, and it's a pretty great language convenience that I can go from a generic class to a non-generic class, or even a non-generic class to a generic class. Now let's go take a look at pair test and see how all this works in action. Let's go ahead and run these tests to make sure that they all still work. Great. Let's start out with pair equals test. I define a pair with string on the left and big integer on the right, and I assign it to the string 1 and big integer.1. Next, for pair 2, I'm going to call the create pair method, the factory method, that just returns new pairs with string 1 and big integer.1. Then I'll assert equals that pair 1 equals pair 2. Of course, the assert equals method is just going to do the equivalent of p1.equals p2. Here I demonstrate to you the shorthand syntax of not having to declare the type twice within the construction. I've got string and big decimal as my two pair types. As you can infer, big decimal is like big integer, but for decimal types like float and double. P3 is going to have 0 and big decimal.0. And P4 is going to be string string and have North Seattle inside. And I should expect that P3 does not equal P4. Makes sense. Let's keep going with some more complicated examples. Here's my triple test. I've got a triple 1, a triple 2, and a triple 3. T1 is just going to be 1, big integer.1, and big decimal.1. T2 is going to be the same thing. And T3 is going to be the string I'll be back. 3 strings back to back. I'll assert equals that my triple is functioning correctly, the equality method for triple, that is, and then I'll assert that, well, this triple is not going to match this triple because they have two different types involved. One kind of interesting thing about generic inheritance is that polymorphism still applies, but of course it really only applies if the parent type is still compatible. So T1 itself by nature being a string and big integer generic type, and T1 being a child of pair with string and big integer, enables me to assign T1 to be in the space of where a pair of string big integer belongs. This is possible, of course, because T1, that triple, fulfills the same interface as pair and then some. So I know that T1 is guaranteed to have the first two left and right fields, string and big integer, so Java is going to permit me to assign it to a reference that expects those two fields. The same thing goes down here for T2. I can still invoke the assert equals method, and even though the references up here are pair types, I should expect to see that dot equals of triple gets invoked on T1, because of course Java is going to go find the most specific implementation. It's going to go find the actual concrete implementation available for the child reference, regardless of how I type the way it's being referenced. We did use class of inside of our definition for equality, so that's going to prevent types from mixing in this case. If I define a new pair, P3, that has 1 and big integer.1, we could argue that the first two fields of P3 equal that of T1 and T2, but because we use that class of method in the definition for equals, we don't get equality between mixed types. Let's go take a look at that definition one more time Control-click on equals. When we check out the class check, we use this.getClass and o.getClass. Remember that getClass is going to return a reference to the actual class definition. So if the two class definitions are not exactly the same, regardless of whether one class is the parent of another, this is going to return false. So in that case, we expect that P3 is not going to equal P1, assert false, because P3 is a pair type and P1 is actually a triple type underneath. Okay, let's go back to the README and finish up here. That very much is generics in a nutshell. And one question that tends to be asked a lot is why not just use object everywhere? We've talked about how object is this top-level global class that all Java objects are going to inherit from, regardless of whether you say extends. So could we just say every type is an object type and just refer to values that way? That's kind of generic, right? I could have said pair object, and then my left and right fields could be assigned to anything. So we could theoretically type all class fields as object to permit any type to be assigned to them. However, upon retrieval, the class fields will be of type object as well. While functional, we lose knowledge of the underlying type. Let's take a look at a silly example. I define a class pair, and this time the left and right fields are both object. Therefore, I can pass in anything into this constructor and get the necessary pair on the way out. So hey, we've got a reusable, generic-ish pair class. Here's an example of it being used though. I declare a new pair with hello world as my two fields. Then I try to look at the length of the left field. And what I actually get is something that's invalid. I'm not allowed to call length on p.left. Why is that the case? Well, I declared left to be object type. Object itself doesn't have a length method. String has a length method, but when I cast these string types into being object types, I lost the information that was telling us that, hey, these types are actually string. This is what generics gives us. By forcing whoever constructs the class to declare the type that the class is going to contain, then in advance, in the future, when I refer to those fields that depend on that generic type, I know that that type is going to be what those values are. Down here though, because I used the top level object, I actually have no idea what the type I constructed this with. When I declare those generic types, the class essentially remembers what the kind of references these underlying objects actually are. Okay, that's all I've got for today's notes. Thank you for listening, and I'll talk to you next time.